Astronomy on tap. Yeah, that deserves applause. Absolutely. Yeah. Thank you. Thank you. We totally deserve it. So tonight we have two really great talks that I'm super excited about. The first one will actually be In a Galaxy Far, Far Away by Dr. Yakov Faerman. And the second talk of the evening will be Rubin's LSST, the greatest movie of all time, by Dr. Zeljko Ivezic. Yes, you can clap for that too, absolutely. But of course, before we get to the talks, we are going to begin with a 10-question round of trivia. So for those of you who have not played trivia with us, the rules are that we're going to put each question up on the screen for 30 seconds apiece. After we go through all of the questions, we will go back through each one of those questions, but only for 15 seconds apiece. So you get 2 opportunities to write down your answer. Now, we are, of course, just a few days out from the summer solstice, which means that this is one of the hardest times to see the PowerPoint presentation. So do you need me to dictate the trivia questions? Yes. Oh, great. Totally wanted to do that. Okay. All right. So with that, let's get started. It says LSST and cosmic distances trivia. Question 1. How long will LSST survey the sky and across what hemisphere? That's great. I wrote that. Answer A is 10 years, and it will survey the southern hemisphere. Question B is 10 years, but it will survey the northern hemisphere. Question C is 5 years, but it will survey the southern hemisphere. And question D is the rest of time across both hemispheres. Okay, question 2. How many pixels does Rubin Observatory's camera have? A, 3,000 megapixels. B, all of the pixels. C, 4,100 megapixels. Or D, 3,200 megapixels. And I'm definitely watching those of you who work in Rubin in the audience, so no cheating. Okay, question 3. Who is the director of Rubin Observatory? A, Mario Juric. B, Zeljko Ivezic. C, Yakov Faerman. Or D, James Davenport. Question 4. When did construction begin on the Rubin Observatory? A, 2005. B, 2010. C, 2015. D, 2018. Or E, 2020. Why is there E? Okay. Or E, 2020. Okay, question 5. By the end of LSST, how much data will it create? A, 500 terabytes. B, 1,000 terabytes. C, 20 petabytes. Or D, 60 petabytes. Okay, question 6. What is the cosmic distance ladder? A, methods to determine the length of galaxies. B, how time travelers move through space. C, methods to determine the distances to celestial objects. Or D, an astronaut training exercise term. Question 7. Who coined the term standard candle? A. Annie Jump Cannon. B. Henrietta Swan Leavitt. C. Vera Rubin. Or D. Helen Sawyer Hogg. Question 8. Okay, is it true that parallax is the difference in the apparent position of an object viewed along two different lines of sight? A, true, or B, false? This question's going to be rough with the diagram. I'm going to get ready to walk. Okay. Okay, this is a parallax diagram that I will describe. How far is the Earth from the sun in this diagram? Okay, so here's what we have going on. We have the sun, okay? And we're looking at the Earth on two different sides of its orbit. Some distance away, D, is a nearby star. And the distance from that star plus the distance from that star to Earth on either side of Earth's orbit has some angle P, which is the parallax angle. Okay, and we measure this relative to stars in the background on the right side of the diagram. Some technical stuff. I think you guys can do it, though. I believe in you all. And the answers are A, 1 AU, B, 2 AU, C, 3 AU, or D, 4 AU, where AU stands for astronomical units. Okay. Just get in there. Okay. Okay, question 10. The first person to succeed at measuring the distance to a star using the parallax method is A, Giovanni Cassini in 1672, B, Frederick Bessel in 1838, C, Frank Schlesinger in 1924, or D, William van Altena in 1995. Okay, so now I will reread all of the questions for a second time. Okay, question 1. How long will LSST survey the sky and across what hemisphere? A, 10 years across the southern hemisphere. B, 10 years across the northern hemisphere. C, 5 years across the southern hemisphere. Or D, the rest of time across both hemispheres. Question 2. How many pixels does Rubin Observatory's camera have? A, 3,000 megapixels. B, all of the pixels. C, 4,100 megapixels. Or D, 3,200 megapixels. Question 3. Who is the director of Rubin Observatory? A, Mario Juric. B, Zeljko Ivezic. C, Yakov Faerman, or D, James Davenport, also known as Jim Davenport. Question 4. When did construction begin on the Rubin Observatory? A, 2005, B, 2010, C, 2015, D, 2018, or E, 2020. Question 5. By the end of LSST, how much data will it create? A, 500 terabytes, B, 1,000 terabytes, C, 20 petabytes, or D, 60 petabytes. Question 6. What is the cosmic distance ladder? A, methods to determine the length of galaxies. B, how time travelers move through space. C, methods to determine the distances to celestial objects, or D, an astronaut training exercise term? Question 7, who coined the term standard candle? A, Annie Jump Cannon, B, Henrietta Swan Leavitt, C, Vera Rubin, or D, Helen Sawyer Hogg? Question 8, is parallax, okay, is it true or false? Parallax is the difference in the apparent position of an object viewed along two different lines of sight. A, true, B, false. Question 9, this is a parallax diagram. How far is the Earth from the sun in this diagram? So we have the sun, the Earth, and then the distance to a nearby star, the parallax angle, and it's compared to the background stars all the way on the right side. The answers are 1, A, 1 AU, B, 2 AU, C, 3 AU, or D, 4 AU. Question 10, the first person to succeed at measuring the distance to a star using the parallax method was A, Giovanni Cassini in 1672, B, Frederick Bessel in 1838, C, Frank Schlesinger in 1924, or D, William Van Altena in 1995. Okay, did you get all of your trivia answers down? Good, fantastic. Please bring your trivia sheets completed and your golf pencils to Sam and Ben in the front. Thank you. And we will be on with the first speaker momentarily. Okay. You can get Sam. Here, I'll take it first. Thank you so much.
All right.
Hi. Thank you.
Thank you.
Thank you. Thank you. Thank you. Sheets. Okay. Oh my God, do we want to mess with the brightness at all? Just see if it can get any better for the dark background?
We can try. It's starting to get more faded.
Okay. I don't know if it was optimized for the trivia slides originally, that's what I was asking. Yeah, yeah. Yeah.
That's a little better, actually.
I think going.
It's a little better.
Yeah. Boy. Yeah, it's a little bit better.
Yeah.
I would go up in brightness, honestly.
Up and
Yeah. That's probably good. I'm guessing that's the best it's gonna get.
Is the aspect ratio right?
The aspect rate?
I mean, I don't think it's showing the whole slide, is it?
yeah, I don't think.
I have Ace Wikipedia. I have the other one. It just said that it was like maybe some stuff would be.
No, it's okay. Sorry, the light is so bad.
There,
Okay.
Yeah.
for this.
That's probably the best it's gonna get. I think that's making it worse. That's good. Like making it better.
That helps, yeah.
Yeah, no, go up in the contrast.
Whoa.
That's really helping.
Yeah. A great demonstration of things. It's not just brightness, contrast too, yeah.
Yeah.
Nice.
Good. Yeah, that's probably the best it's gonna get. Sorry. Okay. You'll have to do a bit of narrating. I said you'll have to do a bit of narrating of the slides. I think it's that light. Ready?
Little tangly.
Should be fine.
Are you looking for it? Oh, okay, that, I forgot you.
Thanks.
Ready?
Is this good for? Okay, cool. Yeah, yes.
Okay. Thank you all for bearing with us while we tried to mess with the brightness settings a little bit. Welcome back from trivia. Hello. Yeah, so the slides, we're all just going to work together to see the slides, and Yakov will provide
Sure.
some captions for
Some.
his slides.
Some.
You'll use your imagination for others. Yeah, I'll get right on that. I'll turn off that light while I'm at it. But, it can only get better as the night goes on. So, with that, it's my pleasure to introduce Dr. Yakov Faerman. Yakov is a postdoctoral scholar at the University of Washington. And tonight, Yakov is going to be giving us a talk titled In a Galaxy Far, Far Away, which will be about measuring cosmic distances. Yakov?
Thank you. Thank you, Megan, and thank you all for coming and joining us here. So my name is Yakov. In my research, I actually I study galaxies and how they evolve and form. But in hindsight, this title may have been a bit misleading because I'm not going to talk about galaxies at all. I'm going to talk about how we measure distances, okay? So let's start. If we go outside the city on a clear night, we may see a picture like this, maybe only brighter, with more stars. And most of the objects we see, of course, in the night sky are stars in our own galaxy, the Milky Way. We can see some other objects. Some exceptions are the planets, which you can see here, of course, Jupiter and Saturn. You can also see, if you're on a very clear sky and very dark sky, you can see our own galaxy, which you can see here, of course, as an arch. This is regions of dust and gas in the Milky Way. But the important thing for this talk is that this picture that you see, the night sky, is of course two-dimensional, right? Because we can pinpoint the locations of objects on the celestial sphere, but not immediately know their distances from us, right? So that will be the main challenge. And of course, one can argue that every picture we see, every image we see is two-dimensional, right? For example, this picture, and we can see a city with narration, with streetlights, no people though. And of course, the thing with streetlights is that we can estimate the distance to them. And we do this by either assuming or knowing that we know their brightness. Sorry, we see their brightness, and we know how much light they emit, which is something I'll refer to as luminosity from now on. Of course, in one simple scenario, we can imagine or assume they're all identical. They all emit the same light. And then the amount of light we see tells us how distant they are, right? That's pretty simple. And this is how we estimate distances. The problem, back to astronomy, is that, of course, stars are not standard candles or not streetlights. And one example for here, you can see here is this star here, Proxima Centauri, which is one of the closest stars to the sun, to the solar system, emits only about 0.2% of the light that the sun emits. Okay, so its luminosity is about 0.2%. And these two stars in the constellation of Orion, which are Betelgeuse and Rigel, emit about 100,000 times the light that the sun emits. Okay? So the very basic problem here is that stars are not standard candles. Their luminosity can vary a lot. And that's one of the challenges. We can't use them as standard candle, right? Standard candles. So once we understand this challenge of measuring distance in astronomy, it's much quieter, it's nice. Once we understand that there's this challenge of measuring distances in astronomy, we can ask two questions. One is why we care about measuring distances, or why it's interesting. And at this point, I'll ask maybe some answers from the audience. Why do we care about measuring distances in the universe, in the galaxy? Some answers. Sorry? That's one good answer, yes. We know how long our spaceship has to go. Other? Yes?
How old is the universe?
That's a good question, yes. How big what? Right, that's another good point, yes. Yes, there in the back. That's a very good question, which we'll get to, yes. Yes, so the answer back there was whether the universe is expanding or contracting. How big things are, that was another important answer. Okay, yes, you need a third dimension to resolve the shape of things. That's an important point. Any other ideas?
Are things moving towards you or away from you?
Okay, are things moving towards us or away from us? Yeah, all of these are excellent answers. And allow me to summarize them. Are there any more things people want to suggest? Okay, cool. So let me summarize these very broadly and very loosely into two categories. One is mapping the universe and the galaxy and maybe understanding our place in the universe through distances, right? So again, mapping, cartography. And the other is distances are very important for understanding the physical properties of the objects we observe, right? For example, how big they are was something that was mentioned, their shapes, how much energy they emit, how much light how luminous they are, okay? Okay, so now that we have some reasons to maybe care about measuring distances, we can move on to the main topic of this talk, which is how we can measure them, okay? And I want to mention a couple of things that we can do, for now at least, to measure them, which is building rulers, sending spaceships, which was mentioned here, not yet, or laser ranging, which is something that was suggested in one of the talks. However, we can do a lot of other things, and some things I'll mention during this talk, or I'll describe in this talk, will be parallax, pulsating stars, and supernovae towards the end. Okay, and I'll maybe mention briefly towards the end that there are a lot more methods, many more, which will not go into, because I heard there's another talk that should be what you were expecting, possibly from the director of LSST, from Rubin or not. Okay, let's start with parallax. So Megan talked about this a bit, but let's make this very interactive. Parallax is the displacement of an object. And let's try this together. Put your arm in front of you. Let's all do this. And now look at your thumb alternatively with your left eye and with your right eye. Okay? Do you see it shifting positions compared to the background, to the more distant background? Yes? No? Maybe? Yes. Amazing. Okay. Sam, you get a good picture? Thank you. Okay, I'll use this in future talks. This displacement compared to the more distant background is parallax. So we're all familiar with this on Earth. But how do we use this in astronomy? And I think Megan also gave a very good background or basics of this earlier. We can use the fact that the Earth is revolving around the sun, and we can measure the position of a given star compared to more distant objects on the sky, let's say in the summer and then again in the winter. And by measuring how much it moves, we can estimate its distance. Okay? So for example, a larger shift would correspond to larger distances. Sorry, Larger shift is smaller distances, closer objects. Smaller angles, smaller shifts are more distant objects. If the object is very, very distant, we won't see any shifts at all. And now, if we know the distance, if we know this angle, which is the parallax, and we know the distance between the Earth and the Sun, which is measured in units of AU, astronomical units, it's probably 1. That's a very convenient thing in astronomy. We can define a unit and then it's 1. That's nice. Anyway, it's about 90 million miles or 150,000 million kilometers. If we know this distance and the angle using simple geometry, we can estimate or calculate the distance to the star, right? And that's the whole idea of parallax. It's very simple. It doesn't do any physical or astrophysical assumptions, right? It's just geometry. And this is the strength of this method. So it seems very simple, right? It's anything but simple because the fact is that stars are very, very far away. Not as far as galaxies, but still. And the challenge is measuring very, very small angles. For example, even the closest stars to the sun, to the solar system, are light years away. And the parallax to them is less than 1 arcsecond. Okay? Just for scale, 1 arcsecond is about the angular size of an iPhone or a smartphone at a distance of 20 miles, which is a fairly small angle. Okay? And we're just getting started. So measuring these very small angles is very challenging. People have done this for about 150 years, but it's still very, very difficult. And here enters Gaia. Gaia is a space telescope launched in 2013, about a decade ago, with the mission of measuring very, very small angles very accurately. Okay? Also, its mission was to measure nothing less than 1 billion angles to 1 billion stars, which is compared to previous missions measuring parallaxes. The previous mission was Hipparchus in the 90s, which measured about 100,000 stars. So this is an increase of a factor of 10,000, which is pretty significant. And Gaia is very good at measuring small angles. The smallest angles it can measure is about 20 parts of a million of an arcsecond. 20 parts in a million of an arcsecond, which is about the size now of a smartphone on the moon. Okay? I'm trying to let that sink. It does that with a digital camera with 1 billion pixels, which is not as good as Rubin, but still pretty impressive. And so Gaia was launched 10 years ago, or a bit more than 10 years ago, and so far it had 3 public data releases, and it has been doing its job magnificently. Okay? It has been, so far in the 3rd data release 2 years ago, it released measurements for almost 2 billion stars, so double what it was supposed to do. And does that very accurately and precisely. This very impressive map you can see here is a map of the Milky Way. So most of these 2 billion stars are in our own galaxy, the Milky Way, with some exceptions. For example, here you can see the small and large Magellanic Clouds, which we'll come back to later in the talk. And remember now, this is not a 2D map anymore, right? We have distances to all these 2 billion stars. This is the 3D map. And the Gaia and the data that Gaia has measured has been very helpful and useful and used for different studies to better understand stars, the structure of the Milky Way, the history of the Milky Way, stellar remnants and different stellar populations, and very different and interesting things. Okay, so Gaia has been very important in astronomy in the last decade or so. However, I want to say that, as I mentioned, most of these 2 billion stars are still in the Milky Way, and we may want to go beyond our own galaxy. And here, maybe a good time to point out that most of the stars we see in the sky don't vary in their brightness significantly, but some do. And these are called, very creatively, variable stars. And they're pretty rare. But the thing is that if you observe enough stars, for example, 2 billion, then you get a lot of variable stars too. And this is the Gaia sample of variable stars of a few 100,000. So we have a sample now of variable stars. So let's look at one specific family of variable stars, which is pulsating stars. Pulsating stars, the reason they vary in brightness is that because the amount of light they emit changes. So they change their luminosity. And they do this because they physically expand and contract. Okay, so their brightness or luminosity change with time periodically. Okay? And the nice thing about this is that if you have a telescope, a camera, fairly dark skies, and some patience, you can measure this pretty straightforward, right? So in this, for example, in this light curve, which is measurements of brightness as a function of time from an astronomer in Greece, you can see measurements of a pulsating star called CY in the constellation of Aquarius. That's not super important. But you can see that it changes its brightness periodically, right? On a scale of a couple of hours, which is fairly nice for a one-night observation. How is this related to measuring distances? At the beginning of the century, comes out this very interesting letter written by Edward Pickering, reporting somewhat weirdly the findings of an astronomer named Henrietta Swan Leavitt. And what Henrietta Leavitt did was observe a sample of variable stars in the small Magellanic Cloud, which I mentioned earlier. And she plotted their maximal and minimal brightnesses. And she noticed, and she measured their period of pulsation. And she noted that brighter stars tend to have longer periods, which is very interesting. Future studies looked at average brightnesses, so not 2 lines. Now we have 1 line. Oh, and I should mention that at this point, the distance to the small Magellanic Cloud was not known, right? So we don't know exactly how to translate this brightness to distance, but we know that stars with longer period of pulsation are brighter, right? There's also the question of here, you might ask, how do we know that these stars are brighter because they're more luminous rather than further or closer to us? And the answer is because they're all in the small Magellanic Cloud, they're all roughly at the same distance from us. Okay, so that's an important detail. So again, so at this point, this relation between luminosity and period of pulsation was not calibrated because we didn't know the distance to the small Magellanic Clouds. But then later on, we found some of these variable stars called Cepheids in the Milky Way. We had the parallaxes to them, and we can place them on the same luminosity, period luminosity relation. Okay, and you can see that these stars from the Milky Way and the small and the large, in this case, Magellanic Cloud agree. They lie on the same relation, and this is very important. Right now, if we have enough patience, we can measure the period of pulsation of these stars, which gives us their luminosity, and given their brightness, we can infer the distances to them. So these are the first standard candles, and really the discovery of the period luminosity relation by Henrietta Leavitt cannot be overstated. Okay, first, these are the first standard candles. So it gives us a measure of distance beyond the parallax scale. And the second important thing is that these Cepheids, these pulsating stars, are very bright, so we can see them to large distances, much, much further than we can measure parallaxes at the time. So this basically gives us the next step of this distance ladder, which we're now building. Okay. Any questions? If there are any urgent questions, feel free to stop and ask me. Yes.
Right there.
So again, I want to differentiate between brightness, which is the light we measure here, and the luminosity, which is how much light is emitted, right? So which one are you asking about? Luminosity. So again, we need to know the distance for that. So given at first, we only know this relatively in the first plot, right? Here we only know that since all of this sample is at the same distance, we know that that these are brighter than these because we see them brighter. And they're more luminous because they're all at the same distance. That's a good question. At this time, this was photographic plates. Yeah. Okay. Thanks. Okay. Yeah. Does this address your question? Okay. Cool. And we can discuss this definitely later. So again, just to summarize them so far, Henrietta Leavitt discovers the period luminosity relation, which gives us standard pulsating stars as standard candles, and allows us to jump or to exit our galaxy to nearby galaxies. And this really can't be overstated because just several years after the discovery of the period luminosity relation by Henrietta Leavitt, Edwin Hubble uses this next step of the distance ladder to do two things. Sorry? Okay. To do two things which are very important. One is to measure the distance to the Andromeda galaxy, which is the next big galaxy outside the Milky Way. And he finds that the galaxy is about 2 million light years, much, much larger than we previously estimated. The discussion just a few years before that was whether other galaxies, or nebulae as they were called, are inside the Milky Way or outside. This answers this question and closes this whole debate. And this tells us that our universe is much, much larger than we estimated before, right? So that's one thing. The universe is much larger than we thought. And the other thing, in a different measurement, Hubble measures the distances to other additional galaxies, nearby galaxies, and their velocities to construct the Hubble diagram of distance versus velocity and find that more distant galaxies recede from us more quickly, more rapidly, at higher velocities, which tells us that the universe is not static, but expanding. Okay? Which is pretty dramatic. And all of this, again, not to stress this enough, all of this is done using the period luminosity relation discovered by Henrietta Leavitt. Once we know that the universe is not static but expanding, the next immediate question would be to ask what happens in the future, right? With different possible scenarios. One is that it stops expanding and reverses its expansion to collapse back to a big crunch. Expanding eternally at, let's say, a constant rate, or increasing the velocity of expansion until all things are very, very distant. We can't see anything, and that's the big freeze. Okay? To try and constrain the expansion history of the universe and infer what will be the future, we need objects that are more distant than pulsating stars. And this is where supernovae come in. Okay, so just a basic, just the basics. Supernovae are the explosions of stars, catastrophic explosions that destroy their progenitors. They usually happen at the end stages of or phases of in the life of stars. And here you can see the pinwheel galaxy before the supernova, and here you can see it after the supernova. Now, in a nearby galaxy, this may not be as impressive, but if you look at other more distant galaxies in images before the supernova in that galaxy happened and after, you can see that often, you can see more easily that often a single supernova can outshine the entire galaxy for a period of time, which is both impressive, I think, and also very useful because we can see them to pretty big distances. So now we have these distant beacons, but the question is, how do we measure the distances, right? And the question is, and the answer is that if you follow, so supernovae are transient events, and if you follow them as a function of time again for, let's say, 100 or 200 days, you can see that their brightness increases at first, but then decreases more rapidly or more gradually. And apparently, while most supernovae have, at least qualitatively, this shape of light curve, specifically one certain type of supernovae, which is type 1a, in another very creative name, can be used as standard candles because, as discovered in the 1990s, the length of this peak is correlated with their luminosity or absolute brightness. Okay, so longer supernovae are brighter, and again, we can use them as standard candles, this time out to very, very large distances. And in the 1990s, two groups independently did this exercise of using supernovae together with other steps in the distance ladder to try and constrain or measure the expansion history of the universe. And another way to say this is they were trying to constrain or estimate how much mass there is in the universe, because in one scenario the universe expands initially, but then if it has a large enough mass, gravity wins and it starts to collapse again. If it has lower mass or lower mass density, it will continue expanding, right? And these were the two main scenarios that these two groups were kind of expecting, either a lot of mass or less mass. I don't think anybody was expecting the third scenario in which the universe starts to accelerate expanding for some reason. But this is exactly what happened. And what they found is that the expansion of the universe is accelerating. And because of this surprise, and because also some contribution by the fact that two independent groups did this measurement at the same time, pretty fast, both groups got the Nobel Prize. Okay, so Saul Perlmutter, Brian Schmidt, and Adam Rees all got the Nobel Prize in Physics in 2011 for the discovery that that the expansion of the universe is accelerating. Again, using supernovae as standard candles. Okay, so this is all I have. And I mentioned at the beginning that I don't measure distances, I study galaxies. So why did I choose to talk about this? And to me, there are three interesting things in this whole topic or subject of measuring distances. One very interesting thing for me was that measuring, I think this demonstrates that measuring a very basic property, a distance, which we may be able to do, for example, on Earth with very different methods and also to some extent intuitively based on brightness of things or size of things, may be very challenging and non-trivial in astronomy, which I think is one of the things in physics in general. The fact that a very basic property can be very challenging to measure is one of the things that attracted me about physics a while ago. The second thing I find really interesting is that this fact that the astronomical distance ladder, right, we went from parallaxes in our own galaxy to pulsating stars in nearby galaxies and then supernovae at the other side of the universe. The fact that it's constructed step by step with comparisons between the different methods and calibration is, to me, really interesting. And finally, as I mentioned a couple of times, and should have mentioned more during the talk, was that both for pulsating stars and in supernovae and the expansion history of the universe, observations and astronomical discoveries often preceded, or empirical discoveries often preceded theory, which tells us how surprising the universe is. And I'll be happy to say more on this if there are questions on this, because, yeah, pulsating stars, I should have said this and I didn't. So yeah, I'll stop here and I'll be happy to take questions. Thank you. Yes.
How do you take into account dust within our galaxy and other galaxies in calculating the luminosity of stars?
So the question was, I'll repeat, the question was how do we take into account dust in our own galaxy for measurements of,
Dust even
right. That's a very good question. I want to mention again that I don't measure distances, so I don't have to deal with dust. Even worse, I'm doing theory, so, okay. I want to say that I can suggest a couple of things, and one is, for example, that we see a lot of stars. So, for example, for dust in our own galaxy, if we have enough stars, then we can map regions that are more dusty and less dusty, and then correct for this. Another thing we can do, of course, is measure not only the light from stars, but also emission from gas and dust in other ways, in the radio, for example. So that also helps us to estimate the presence of dust. And finally, briefly, I want to say that the color of things also tells us something about dust, the amount of dust, because it affects different wavelengths. So yeah, so there are different methods. There's not a single thing. Yes, and we'll continue back there. Yes.
We didn't talk about direct measurements of motion or velocity.
I didn't. That's true.
Are any of the techniques able to actually measure velocity?
Yes, that's a very good question. So the question was whether there are any techniques that are able to measure the velocities of objects, right? That's good? Okay, thanks. Again, I don't want to be rude or disrespectful to people who are doing actual difficult observation of things, but I want to say that measuring, for example, velocities is kind of easier in a sense than measuring distances, because, for example, you have the Doppler effect, and if you have emission lines or absorption lines, then we have the shifts of these spectral lines, and we know their, let's say, wavelength on Earth. We can measure their observed wavelength, and this is how we know velocities, right? So again, it's not, I don't want to give the feeling that it's easy, or like some people spend a lot of time on this, but it's not, it's a different challenge than measuring distances. We have ways of doing that well. And I did kind of skip over that, yeah. Yes?
What percent brighter and darker they get? Is it like is it significant or is it like 2%?
Oh, okay, that's a good question. So the question was, I'll address the second question first. Whether how much do variable stars vary? Is it by 2% or more? And this is something that I, of course, avoid going into because this is a lot of astronomy. But I can see the units anyway. This is excellent. So the variation is measured in magnitudes, which is logarithmic unit of brightness. And it depends on the exact variable star family, but they vary significantly. It's not a few percent. It's often a factor of 2 or so, let's say. Or, yeah, tens of percents at least. Yeah.
In your example, the bigger stars were brighter. Is that always the case when the first one?
Ooh, I should know this, because I want to say that the two things that set the luminosity are the temperature and the size, right? So it kind of depends on the interplay of those two things. And if you have more surface area, you emit more light. But actually, the total luminosity depends much more strongly on the temperature. So it kind of depends on on how the temperature changes with size. So it's not, yeah. It's a good question. Yeah. Yes. When does it become, sorry? I can't hear the last part. Not useful in the sense. I see. Okay, so how far out can we measure parallaxes, basically? Yeah. So again, this is this is very much depends on your how well you can measure these small angles, and for this, I think this is actually shown in the last slide. Our horizon expanded significantly with Gaia, and Gaia can measure distances to. Sorry. This is magnitude, but we're thinking of, yeah, so I think kiloparsecs at least, which is thousands of light years, which is a lot more than before, but still fairly small region of the galaxy, I want to say too, yeah. I think, oh, sorry, this, yeah, okay, this is shown here, right? You can see this is exactly this. This is the old parallax limit, this inner circle, and this is the new one, which is, again, I would say a few kiloparsecs, or a few thousand light years, yeah.
Been a thought to move Gaia out to like Mars's orbit or Jupiter's orbit to get a much bigger base for calculating them pair limits?
You're asking whether there was an idea like that? I have not heard about this. I don't know if anybody here else. Oh, you mean, so yeah, I want to say moving it's probably not an option. Initially sending it there is a good question. I want to say it probably gives you a factor of just a few. Whereas again, the technology enabled you a factor of like 1,000. So, yeah. Sorry. Money. Okay. Any other questions? Okay. Thank you so much.
From you?
Oh yeah.
You can give that to them. Thank you. Okay. Don't move yet. I'm gonna quickly announce the LSST and cosmic distances trivia answers and winners, and then we will have a brief intermission. We'll come back for the second talk of the evening. If you win trivia, do not come get your prize now. Wait until the end of the second talk, please. Okay. Question 1. LSST will survey the sky for 10 years across the southern hemisphere. 2. Rubin Observatory's camera has 3,200 megapixels. Zeljko is the director of Rubin's Observatory, and he will be giving our second talk of the evening, so it's very exciting. 4. Construction of the Rubin Observatory began in 2015. By the end of LSST, it's projected to create as much as 60 petabytes of data. The cosmic distance ladder, as you know now, is methods to determine the distances to celestial objects. Henrietta Swan Leavitt coined the term for standard candle. It is true that parallax is the difference in the apparent position of an object viewed along two different lines of sight. The Earth is always 1 AU from the sun. Always is. And the last question, Frederick Bessel is the first person to succeed at measuring the distance to a star using the parallax method. So we have 2 runners-up who got 8 out of 10 questions right. And we have 1 winner, first place, that got 9 out of 10 questions right. So our first runner-up is Alpha Wolf. Nice. Our second runner-up is Nabo. Nabo. And finally, our first place winner is Weller and Weller. Well done, Ben. So with that, let's go for like a 10-minute intermission. And with that, we will go into our second talk of the evening. So our second speaker is Dr. Zeljko Ivezic, and he is the director of the Rubin Observatory. He is also faculty at the University of Washington. And he pointed out to me during the break that Earth is not always 180 from the sun because it is on an elliptical orbit. But luckily for me, I already passed my candidacy exam and the paperwork has already been submitted. So you can't change it now. Okay. And with that, Zeljko.
Thank you, Megan, for a wonderful introduction. Thank you all for coming tonight to listen to astronomy. As an astronomer, I'm always thrilled to see people who are not astronomers being interested in astronomy and in science in general. So if you would humor me for a moment, if you are not an astronomer, can you raise your hand? Thank you. And raise your hand if you are not in any STEM field, if you STEM. Science, technology, engineering, and math. Okay, we have a lot of non-STEM people. Welcome. And I'd like to start by saying thank you to our wonderful grade students who are doing this series because they are interested in astronomy. They love astronomy. They don't get paid for it. They just love doing it, and they do it almost every week. So let's thank them. Okay, so in a few minutes that I have tonight to spend with you, I would like to share some excitement about a new observatory that is coming online in Chile, but it's public national US observatory. It's being built in Chile because observing conditions are better in Chile. There is too much light pollution in continental United States. And so this is a short video clip made by our Air Force. We have Air Force in Rubin Observatory. We have 2 little drones. And so this is just to give you an idea about how does it look like when you go far out at this is 3,000 meters in funny units. That's 9,000 feet. So it's about 9,000 feet. And you can see there is no vegetation. That's on purpose. We select places in the mountains that are high, that are dry, and that have stable atmosphere. So why are we building this observatory? If you listen to trivia questions and you knew the right answer, it's 2015 when we started building it. And that's the year when we got federal funding, the majority of funding. But actually, we started design of that observatory 20 years ago. And so here it is. I don't know if you can see the slides. Usually I tell my colleagues from other fields, it's easy to give astronomy talk. You just show beautiful images of the sky and you talk to them. But today, this will be horrible talk because you can't see anything. So at the top of this slide, there are a few modern observatories that are either being built or are already in operation. In the top half, you can see, top right half, you can see James Webb Space Telescope, which is already in orbit, and next to it, Nancy Grace Roman Space Telescope. So both of these are spacecrafts, and they continue Hubble legacy. So they are improving on Hubble in 2 ways. James Webb Space Telescope has a larger mirror, 6.5 meters instead of 2.5 like Hubble. And the one on the right that will be launched in a couple of years will have a field of view 100 times larger than Hubble Space Telescope. So that field of view is how big chunk of sky you can see with your telescope. So Hubble Space Telescope cannot even see the area of full moon, but Nancy Grace Roman will see much larger area of the sky. And so this analogy translates to ground-based telescopes. So the 3 big ones you can see. So this is European telescope, European Extremely Large Telescope. That's the name. They couldn't think of anything better. It's 40 meters across diameter of the mirror. It will be the largest telescope ever built in human history. And these two that are slightly smaller, they're 30 meters or 100 feet across. They are led by US institutions. And these 3 telescopes, they're equivalent to James Webb Space Telescope. They're pushing the mirror size in order to be more sensitive. On the other hand, our telescope, Rubin Observatory, is pushing the field of view size just like Nancy Grace Roman Space Telescope is pushing. So that is different telescopes. And so that answers this question that you can ask, why do we need all these telescopes? They are expensive. Indeed, Rubin Observatory is the least expensive telescope on this slide. It's only about $1 billion. Your money, your tax dollars. Thank you very much. The other ones are even more expensive. It goes up to $10 billion for James Webb Space Telescope. So why do we want to build yet another telescope? For example, it works out that for the price of Rubin Observatory, you could buy a 6-pack of beer for every American family. Would that be better than building a new telescope? No, you just peak tomorrow, and this will have a lasting legacy that I'm going to tell you about. So why do we need different telescopes? Well, this is a good analogy. All these vehicles have 4 wheels, they have steering wheel, a person can drive them, they have an engine, yet they look different. They look different because they're optimized for different things. One is very fast, the other one is very strong, and the third one can carry many more people than the other 2. So you optimize for certain function, and indeed, Rubin Observatory is optimized for a very large field of view. So typically, a big telescope the size of Rubin telescope can see part of the sky that is smaller than full moon. They can see roughly the area of one of these little squares. Can you see little squares in the slide from the back? And oops. So these little squares, they are sensors in our camera that I'll show you more about later. And this big circle, that's the field of view of Rubin Observatory of Simoni Survey Telescope. It's 100 times larger than equivalent telescopes. That means if you wanted to cover the entire night sky in one night or few nights, you could do it 100 times faster than with other telescopes. So what we do in 3 nights, other telescopes would need to do in 1 year. And our program that I'll tell you a little bit about that will last 10 years, it would take 1,000 years with existing telescopes to accomplish it. Basically, that means it's impossible to do it with other telescopes. 10 years is roughly the right time scale. For example, if you count on grad students, they graduate, they become unruly, they leave program. So you go up to 10 years. So that was my introduction. So now I'll spend 5-6 minutes on each of these 3 topics. So what I want to tell you is just a few words about science, about justification, about motivation for building this new observatory and for undertaking this new project called Legacy Survey of Space and Time. That will be essentially a movie of the night sky collected over 10 years. Then I'll spend a few minutes showing you, I hope you will be able to see it, showing you some pretty pictures about how we are building this observatory and what are the main components of the observing system. And then I'll conclude with a few words about what we are doing at the Astronomy Department at the University of Washington, what is our role in this project. Indeed, the University of Washington was one of the 4 founding institutions of this project. And by today, we have over 40 US institutions working together with federal funding. And in our science collaborations that include people preparing to do science eventually with this data set, we have over 100 institutions around the world, more than 30 countries, and few thousand scientists are already preparing to do science with this data set. So let me tell you a little bit about science motivation. We have 4 main science teams, and I can't go into all of them, so I'll emphasize one that is probably the most important one, the cosmology. Generally, in astronomy today, we are trying to answer 2 big questions. We are trying to ask, is there life on other planets? Obviously, that's a huge question. If we found life on another planet, that would change everything, not just science. It would change philosophy on Earth. It would change our view of religion for many religions. It would be a major change. And that's why we are all excited about the fact that today technology is becoming so powerful that we are at the brink of discovering life on other planets if it exists. But I will not tell you much more tonight about it, because our project, Rubin Observatory, is focused on this other big question, which is understanding the universe. Why is the universe expanding? Why is it accelerating when it's expanding? What does it mean for fundamental physics? And so you already saw in Yakov's talk, this gentleman, Edwin Hubble, one of famous American astronomers who discovered that the universe is expanding, and that expansion velocity is proportional to distance from us. That's what this diagram shows. And good analogy is a loaf of bread that is rising because of yeast. And then if you imagine it's a raisin bread, each pair of raisins will be going apart from each other, and velocity with which they will be moving away from each other is proportional to their distance. And so that means, it doesn't mean that we are in the center of the universe. It means that the whole universe as a whole is expanding like this loaf of bread. So we knew that for about 100 years since Hubble discovered it. And then there was this huge surprise 20 years ago that Yakov also mentioned with that Nobel Prize, when people discovered accelerated expansion of the universe. That was huge surprise because we didn't expect it. The only force that we know of that acts on these large distances is gravity. And so now if you have galaxies moving away from each other, the only thing that can happen is that gravity will slow them down. It's as if I took this pointer, I threw it up. You would expect that it will come back to me because it's losing kinetic energy due to gravity of Earth. It stops, it comes back to my hand. And what we observe in the universe is this pointer going faster and faster away from me, almost like it had a little rocket engine that was accelerating it. But we don't know what is that rocket engine for the universe. And so we have two ways of explaining what could be going on. One is, if you assume we understand gravity, and that's Einstein's theory of relativity, then you would think that there is some mysterious new constituent of the universe, some fluid called dark energy. You stick that new component into equations, you explain everything that you observe, and you're happy. But another possibility is the theory of gravity is wrong. And our conclusion is wrong that there is dark energy. Maybe there is no dark energy at all. We just need to fix theory of gravity. And it won't be first time. Einstein fixed theory of gravity that Newton developed, which does not explain things when they move very fast, when they have a lot of energy. You need to introduce theory of relativity. But maybe theory of relativity is not perfect theory. On these cosmological scales, you need to modify it. So which of these two is more likely? We don't know. We don't know because our data are not good enough. What kind of data? This is one example of modern astronomical data from Sloan Digital Sky Survey. So each dot in this diagram is one galaxy. We are in the center. Think of a pomegranate, and you cut it with knife into two halves, and now you look at the structure of one half. And these seeds in pomegranates, these are like galaxies in this picture. And the main point is that these dots are not randomly distributed. It's not like as if you took a handful of sand or salt and threw on a table. There is very clear structure. You can see that some parts are very dense, and then there are these voids where there are almost no galaxies. When you describe this pattern statistically, you can tease out the physical properties of the universe. So what you need to do is to observe many galaxies across the whole sky very sensitively so you can see very, very far out. And then you do your statistical analysis of their distribution in space, and you can then figure out if your theory of gravity explains everything or you need to modify it, together with some other observations that tell you how fast is universe accelerating and expanding, that supernova measurement that Yakov talked about. So this is what we have today. And although it's an amazing data set, 20 years ago, this data set would have been like science fiction. This was all collected over the last 20 years. But it's not good enough to answer this question, was Einstein wrong with his theory of gravity or not? These data are not good enough. What we need to do is to see more galaxies, to go further out. Instead of 100 million galaxies, like in previous slide, we need about 5 billion galaxies, as many galaxies as people living on Earth. And so you need to go and see more sensitively, very far out to faint objects. And for that, you need to have either very huge mirror, even bigger than 40 meters, or you need to observe many times each object and then average observation. And that's exactly what Rubin Observatory was designed to do. So as a comparison, this is an image that was used to construct this map that I show you of those galaxies that look like pomegranates. This is teeny tiny piece of sky, smaller than full moon. So that's standard today. What we want to get with LSST on Rubin Observatory is something like this. This is a real image. This is real image too, of the same part of sky. But this one is telescope with 2.5 meter mirror, SDSS telescope. This is Japanese Subaru telescope that has the same size mirror as Rubin, but it has much smaller field of view. So that Subaru telescope would need 1,000 years too to obtain data set that we will have in 10 years with Rubin. But for this tiny piece of sky, you can see what will change. From this today, we will be much more sensitive and see more objects. So I love these two slides. These are my favorite two slides in the whole presentation. Whenever I get tired of sitting on Zoom or going to meetings or waiting at the airport, then I go to these two slides and this gives me strength. Thank you, thank you, thank you. So let me conclude this first part. So this is Vera Rubin. So Rubin Observatory is unique because it can see 100 times bigger piece of sky than any other similar telescope. That's one thing to remember for this part of the talk. This is Vera Rubin. Why is the telescope or observatory, not telescope, observatory named after her? She was the first astronomer who provided convincing evidence for the existence of dark matter. So she measured motions of stars in other galaxies, and she showed that they move as if there was more matter than we can see in photons, in light. So there must be something out there in other galaxies and our own that produces gravitational force, but it does not emit light. And because it's gravitational force, we call it matter. Because if there is no light emitted, we call it dark matter. We don't know what it is, but there are some good candidates from particle physics theory. Unlike dark energy, where we have no clue what's going on. So Vera Rubin also was great advocate for women in astronomy. There is a famous story when she was the first one who observed at Palomar Observatory in California. She was denied access to the telescope, even though on scientific merit she was awarded time, but the director of the observatory at the time told her, you could not come observe because there is no female bathroom. But there were two men's rooms, so she came, cut out shape of a woman out of paper, stuck on one door and said, you see, there is bathroom. And she was the first one who observed. Things change. Our department, astronomy department and University of Washington, is extremely proud that of all the largest departments in the world, we are the only one who has half and half female and male faculty. And we have more female graduate students than male graduate students. So let me now spend a few minutes showing you how we are building this observatory. So this is our team. We have a few hundred people who have been working for well over a decade building it. So the observatory itself is in Chile. It's about 1 hour flight north from Santiago. It's at -30 declination. Those two lines, if you see them, they are fiber optical cables that will ship the data from Chile to US. Entry point is in Florida, and then it travels to California to SLAC laboratory, where our data center is. And then it immediately gets sent, copied to France and UK, who will do additional processing and also serve as backup. So this is zoom in of that region in Chile. I don't know how much you can see from the back, but there is a small tourist town called La Serena and harbor Coquimbo next to it. It's about an hour drive up the mountain to the entrance of protected area that is being rented by Association of Universities for Research in Astronomy. It's a US organization that does astronomy on behalf of federal government. And then there is another hour going up the mountain to the observatory, and that was that drone video from the start of the presentation. So now I'll spend a minute and a half showing you accelerated 10 years of building the observatory. I don't know if you can hear the music. So we had to level the hill. And then there is a little hill on the right, that's for auxiliary telescope. On your left, you can see observatory drawing. This was about a decade ago. So this is the main pier, isolated from the rest of the observatory because of the vibrations. We were supposed to be done in 2022, and then COVID kicked in. And so for 2 years, we couldn't get workers to the summit to finish this dome. You see this big green or cyan cylinder that's going to become the dome. Now you can see it, it's completed. And so we lost 2 years. We are going to be done next year and start this 10-year observing process. So that's the. So let me now show you a few slides about technology. There are some nice, notable technologies built into it. The mirror itself is a unique mirror. It's actually two mirrors. The outer edge of this mirror acts as primary mirror. The inner part where these four people are sitting is tertiary mirror. It has different figure. It's more concave. And that mirror was produced in a spinning oven. Around it, you can see this red part. That's the wall of the oven that was put down, but it's vertical. And then there is a lid that goes on top. And so you put pieces of glass as big as a six-pack of beer, good analogy, and then you melt them and they become liquid. At the same time, the oven is spinning. And then because of spinning, you get parabola for the free surface. Try with your glass of beer, don't get wet. But if you rotate it, you will see that you get parabola on top. And then you cool it down for about 4 to 5 months, very slowly, and then it solidifies, and you are left with almost perfect figure on top. And so that's the telescope. This is a picture from Spain, from the factory where they did it. Then they disassembled it into 10,000 pieces, shipped from Spain to Chile, reassembled, and why is it not working? I think if you click, is someone controlling? Yeah. Let's start the movie. It's a 300-ton telescope. It's the fastest telescope of that size ever built. It has to move fast because we don't want to lose valuable observing time on slowing from one part of the sky to the other. So this whole thing, when it moves, it draws 1 megawatt of power. It's like hundreds of houses at the same time. We don't have that power. We don't have power lines that can transmit megawatts to the summit. So what we have is like giant batteries that are inside the observatory. So you charge these batteries, then you use the charge to move it fast, and then when you brake, that charge goes back into those batteries, just like a Prius, but it's much bigger. And we don't observe anymore through the telescope, through the eyepiece. I know you all know that. So not like those two kids in the bottom of the slide. What we do is we have sensors like in your telephones, CCDs, charge coupled devices, that then can display these images just like you display it on your phone. We display it on these big screens to follow what is happening with the observatory. And so this is the camera that has this sensor. It's fairly large. It is the largest camera ever built. This logo on the right is from Guinness Book of Records. It is officially in the Guinness Book of Records as the largest camera. It's 3,200 megapixels. That was also on our trivia today. You can see to the left, this is former project manager Nadine of the camera. She was exactly the same height as the diameter of the camera. She made this diagram. How do you build the largest camera in the world? Well, first you have to split it into smaller pieces, and then each team that collaborates gets one of these pieces, and they find experts that can do electronics or mechanical work, etc., refrigeration, and they together work on individual pieces, and then they integrate at the end. It's very complex instrument, so integration is very complex, and that's why you have million Zoom calls to talk to each other and make sure it all goes well. That's when it's done. This was about a few months ago, still in California in the lab. And then it was shipped a month ago to Chile. Now it is safely in the observatory in so-called clean room. And we are now testing that everything went fine with electronics when we shipped it by Boeing 747 from San Francisco to Santiago. And then we trucked it from Santiago to the top of the summit. That's the happy team of physicists from SLAC Laboratory who designed and built the camera with the help from a few other government labs. It's clean rooms, so they're all wearing bunny suits. It's very clean. In the back, you can see the front lens, the entrance to the camera. This is closed up. This is the largest lens ever produced. If you are amateur astronomer, you probably know about Yerkes Observatory and the fact that they used to have the largest lens. They have the largest telescope refractor with 1 meter, little bit over 3 feet across lens. But now for our camera, we needed to produce 1.7 meter lens, and that's this one on the slide. That's the focal plane of the camera. So that's the eye, just like fly. When you look at fly's eye, you can see many different sensors. This one has 189 sensors for science, plus 12 more in the corners to control image quality, to measure how deviations from perfect image quality, and then you give instructions to actuators, over 100 of them that control the figure of the mirror to keep mirror in perfect shape during motion on the sky. And it works. So this is real image, so-called pupil image without telescope of an old photograph of Vera Rubin. And she's working on a measuring machine. And so the image itself was produced with this new big camera with 189 or 2 and 1 sensors. And it's very hard to convey to people how large that camera is, because you can't see all of that detail with your eyes. Your eyes, they don't have 3,200 megapixels. Depending on how you define it, they have maybe 500 megapixels. So there is no way for you to see the whole image. If you wanted to display it just like we display television images, so that it's adjusted to the angular resolution of your eye, about 1 arc minute, it would take 1,500 television screens put together to display one image from that camera. And so this is, of course, in PowerPoint. This doesn't exist. This is just to illustrate. But as of recently, as of last October, when U2 band opened the Sphere venue in Las Vegas, they are now the largest display in the world, and they can display 1/2 of our image. So that's how large that image is. And so let me now conclude with a few minutes of what we do at University of Washington. This is image of our classroom building. I put it in instead of the other building. because you can see this little disc-like structure that's our planetarium. We do have, I think, once a week, you can come to planetarium, and if you're interested in astronomy, you can have a great show in planetarium. It's on our webpage, just Google for it. And it's also run by grad students, and it's excellent. So what we do at UW in the context of Rubin Observatory is mostly software. And we have about 20 people who are developing so-called alert pipeline. What that is a piece of software that will subtract images, two different images obtained at different time of the same part of the sky, to compare them to see if anything changed on the sky. So traditionally, people have been doing this in astronomy for almost a century. Clyde Tombaugh, who discovered Pluto, former fame as a planet, not anymore, but used to be a planet. And that was done mechanically with two images that were with a so-called blink comparator, where a mirror would flip two images, and then you would see that something's moving. But here we do it in computer. So you can think of it as subtraction pixel by pixel of two images of the same piece of the sky. It's much more complicated than that. That's why we have 20 people who've been working on it for many years. It's much more complicated because the angular resolution changes as atmosphere changes, transmissivity changes, and then as you observe at different distances from horizon, your thickness of the atmosphere is different. And then it acts like a spectrograph, and then what it changes depends on the color of the object, and so on and so on. It becomes a horrible mess. And it takes a lot of algorithmic development to make a pipeline that is both robust, fast, and accurate. And so that's what we've been doing here. And the goal is then to automatically process every new image that we get from Chile to California. We process it within 60 seconds. We find what changed on that image compared to previous images, and we report it in a web stream using Kafka Stream to everyone in the world who wants to connect and ask what are the new objects, new supernovae, what are the changes of variable stars, what are the new asteroids on the sky, new comets. You can get all of that from that stream, and then you can take other telescopes like these on the picture in the bottom, and you can get additional observations depending on what kind of object you're after. One of these interesting objects are asteroids, and today we have about 1 million known asteroids. Since 200 years ago, when the first one was discovered, today we collected about 1 million of them. With LSST, over about 2 years, we'll get another 5 million. In a couple of years, we'll get 5 times more asteroids than in last 200 years. And there is a special kind of asteroids called near-Earth objects that potentially might be on an orbit that will bring them to collision with Earth. And so we don't know today of anyone that is on collision, but we do know that there are about close to 100,000 such objects that are larger than about 100 meters, 300 feet, that would cause major catastrophe on Earth if they struck, and we don't know their orbits. So the goal that we will achieve with LSST is to catalog them all, compute their orbits, compute probabilities for collision with Earth, and hopefully none of them will be on impact trajectory. If it is, then again, there are mitigations that we can undertake. But first, you need to find them and know that particular object is on dangerous path. So are there any data scientists in here? Just one. Oh man, this slide's for you, man. So I wanted to conclude by pointing out that with this large data set and all these automated software pipelines, we get these catalogs, but we don't print them anymore. You could go to astronomy library, find catalogs with printed data for objects. We can't do that with 40 billion objects in this data set. It will be for the first time in history that astronomers will have cataloged more objects than there are living people on Earth. We could literally name a star and a galaxy after every person on Earth, even after you. So with new, different way of doing astronomy. You have a database. You don't go to the mountain. You don't go observe yourself. You have these observations in database, and then you ask questions. It's a different paradigm. Traditionally, if you work in science, we all learn in kindergarten, you formulate your hypothesis, then you design your experiment, then you try to reject that hypothesis. We don't do that anymore with these databases. We have data, you have to ask the right question, and then you answer with this database. And so, given the size of database, it's a non-trivial undertaking. So we will be measuring roughly 10,000 numbers per object. So you can think of this, you can't, but you could think about 10,000 dimensional space. Nobody can think about 10,000 dimensional space. So we have to teach computers to do it. So in that 10,000 dimensional space, it's populated with 40 billion points, 40 billion objects. And now we want to do something with it. And what we want to do with it is what we do today with smaller data samples. We want to cluster it, we want to classify, look for outliers. This is what we are already doing today. But we are not doing it in 10,000 dimensional space with 40 billion objects. And that's something that we are doing at our department. There is an institute called Iraq, and we specialize in that kind of work. And we are honored tonight that the founding director of the Iraq Institute is with us. And I'll leave you to recognize him. He's a well-known guy. He was on front page of Seattle Times, TED speaker. You'll recognize him after the talk. And he's my BFF. So I will finish here. Thank you very much. So if there are any questions, I'll be happy to answer them. One here.
Some point, because things like camera, megapixels, all that constantly shift. At some point, you have to say, oh, this is what we're going.
Correct. So first, there was a compliments to the architect. Yes, our first design of the observatory looked like a house on stilts. It looked horrible. But when you're on government budget, you have to make it the cheapest we can. And we didn't like it. And so then we came with that ingenious idea. You know, when we observe, we have to have stable atmosphere, because then the resolution of the image is bad if you have turbulence and so on. And so if we had a beautiful design with smooth roof oriented towards the predominant wind direction, our atmosphere will be very stable. And so that's how we justified redesign. And then a Chilean architect came up with this beautiful Sphinx-like design. Now, you said, did we have to freeze technology? We did, especially for hardware. So like we had to order those 200 sensors. We started 10 years ago. It wasn't obvious that our requirements will be met. So we had two vendors, one in UK, one in Arizona. They both met our requirements, but they couldn't produce the number of these sensors that we needed. So we ended up with two types. We got a little bit over 100 from one and the rest from the other one. So that was frozen. One thing that is not frozen, and it cannot be frozen, is software. So we are designing software in such a way that basic algorithms are implemented in a modular way, and then middleware around them that allow us to run it at scale. That is changing, and it will be constantly changing. So now we can go easily from cloud-based design, like we go to Google Cloud or AWS. We can go to our own data center in California and run exactly the same software. And this way we can go back and forth. I see hand in the back. Could you repeat? It's hard to hear. Oh, how's the mirror cooled? So there are several things we have to cool. So we have to cool mirror. The reason for cooling mirror is this image quality. If mirror is warmer than ambient temperature, then you get the same effect as on a summer day. You look down the street and you can see how things are moving because of the air motion. So that's cooled with air. We have a giant AC system in the observatory, and then there are pipes that bring cold air to the mirror, and they are of the order 1,500 little points that go into basic cells that keep structure of the mirror. And that's how mirror is cooled. The camera itself has to be cooled too. First, you have to cool electronic boards because they produce heat. And then you also have to cool sensors because if they are not cooled, they have so-called electron Thomson noise. You get something like snow on TV. Those of us who are over 60, we remember all TVs with snow, right? So that's what happens. And so you need to cool it down. And so there is one refrigeration system in the camera that cools the sensors to minus 100 centigrade. And then there is another independent system that cools electronics to minus 40 centigrade. There was a hand over there. Auxiliary telescope helps us measure the transmissivity of the atmosphere. As the light goes through the atmosphere to the main telescope, it's absorbed depending on distance from zenith and on color, but it goes from 10% to even factor of 2 absorption. And then you need to calibrate observations. So in order to know, and that changes from night to night. And so in order to know on particular night what is the change of transmissivity, we have smaller telescope that has different instrument that looks at known stars where we know the answer without atmosphere from previous observations. And then we observe it tonight. And from that observation, with comparison to what it would be without atmosphere, we know what atmosphere is doing tonight. And then we use that information to calibrate the main images. Hand in the back.
You said you started working on this about 20 years ago, and about a decade ago, we learned about the expansion, the accelerated expansion of the universe. So, was it just like convenient that you were working on this thing that would help answer that question, or did the design change when that information became known?
Oh, that's a wonderful question. Yeah, excellent question. So, how did we know 20 years ago that there is dark energy? We didn't. At that time, the main driver in cosmological context was dark matter. So all the observations, all the design that we wanted to get was driven by dark matter. And then also there was other astronomy we wanted to do, like stars in the Milky Way, asteroids, etc. And that all was justification for the project. And then you could say it was a godsend that they discovered accelerated expansion, because then there was even more motivation for the observatory. And that's actually how Department of Energy and high energy physicists became interested in Rubin and joined the project with their funding. So it accelerated and made the funding more robust for the observatory. I think we would have succeeded even without the discovery, but it was certainly great help. In the back there.
Geopolitics related to building a $1 billion thing in a foreign country?
Depends on the country. So, like, if you wanted to build it in North Korea, that would be a lot. So, Chile is excellent for astronomy. So, the first observatory was started by US in late 50s, early 60s, and then Europeans joined. So, today, if you look at the area of mirrors in telescopes, Chile has more than half of all the telescopes in the world. It's like the country capital of the world. And they did have some dictatorship in past and so on. But even during that time, it was easy to do astro business with them because they are supportive of it, because it brings revenue, it brings technology, and they even have agency in their Ministry of Science dedicated to astronomy and astronomers. So Chile is fantastic for doing work within astronomical contest. Now, in some other countries, it can be harder. Even in US, it's hard. In Hawaii, one of those 30-meter telescopes is not built yet because they ran into problems with natives in Hawaii, partially due to astronomers, in my opinion, being arrogant at the beginning of the project and not talking to people there. But it didn't end well, and they are still without confirmed site. So, and that's US, that's not foreign country, and it still is problematic. So it's good question, depends on details. Yes, sir?
How upgraded is the technology inside? I understand the software again. How about the hardware?
Yeah, so the question is, how upgradable is the system? Or another way of asking this question, maybe not exactly the same, but similar, is what do we do after 10 years? So we had some thought about it. So the easiest thing to do is just to say, well, these first 10 years were great. Let's continue doing for a few more years what we are doing. Another option is to say, well, we did it with these 6 filters. We have 6 filters that block the light in particular way. You could say for some other programs, we need slightly different filters, so we put different filters. Or you could go even one step further and say, well, this camera is 10 years old, technology changed, sensors improved, let's build new instrument, whether it is camera for images or spectrograph or something third. That would be even more expensive step. We think telescope by itself will remain robust for 30, 40 years at least, because it's just basic optics. But all these electronical things, they could be upgraded probably. Ideally, one day, long after we are dead, maybe someone will discover a way to make a sensor that will capture photons, and it will know which wavelength of the photon, which energy photon had, so we don't have to use filters. When we observe, we have 6 filters that are roughly the same width. So when photons come, we put this filter, 5/6 of all the photons we throw into garbage. They're blocked, they heat filter. Only 1/6 of all these photons we capture and learn from them. That's wasteful. So if we couldn't build a sensor that would not block them, but take them all in and just record what was the energy, that would be great. And indeed, at the laboratory scale, there are already such sensors. It's just we cannot make them so large that we could use them in a practical sense. Last call for David. And I told him, be careful what you ask me, because next time we talk, I will be on your graduate exam committee. I'll be asking questions.
My question is, when will the data start becoming available science-wise?
Okay, wise question. Wise question. So next January, we'll get first images from our camera on the sky images, not like the one with Vera Rubin laboratory. We'll put it on the telescope and then observe. And by the end of next year, we hope to be done by construction and start LSST observations. From that point on, it will take a year to get first public data. It will be 6 months to collect the data and 6 months to process and make it available. So I would say, roughly speaking, by late 26, fall of 26, we should have so-called first data release. And now that you reminded me, I did not do justice to, again, to Seattle and this area and their contribution to Rubin Observatory. So I already told you, University of Washington was one of 4 founding institutions. We also have a strong team at the Department of Astronomy. There is one other connection through Charles Simoni. The telescope is called Simoni Survey Telescope. So before we had federal funding, when we had to purchase mirror from University of Arizona, we had to get it because it takes many years to get that mirror. It was about $30 million that we didn't have. And so then Charles Simoni and Bill Gates stepped in. Charles Simoni is also from Microsoft. He was the lead of the team that developed Microsoft Office, and he's also a benefactor to Seattle Opera, Seattle Art Museum, to education in music in Seattle, etc. So he stepped forward and he talked Bill Gates into helping, and so they gifted us $30 million to purchase that mirror that allowed us to stay on schedule. And that was very significant at that time when we didn't have federal funding. So that's another Seattle contribution. So I'll stop here. Thank you very much.
Thank you, John. Thank you.
Thanks for inviting me.
Yes, my pleasure. Okay, let's have one more big round of applause for both of our speakers this evening. And I have just a few things to say before I release you all. Thing number 1 is, if you're from the University of Washington, we'd love to take a group picture. Okay. Thing number 2 is I just want to remind everyone that today is a holiday. It's Juneteenth. That's becoming well known as another Independence Day for America when enslaved people were freed. So I just want to remind everybody that that is the heritage that we need to remember today. And then finally, the next 2 months, July and August, I will be taking a hiatus from emceeing astronomy. I know, it's so sad. Let me hear your boos. Thank you so much. That'll be getting me through the next few days. Yes, it's true. But Sam will be emceeing again, so now you can applaud. And I will be back in September. All right. Thank you. Thank you. All right. With that, thank you all so much for coming tonight. And what? Oh, good question. Good question. July 24th, next month at 7 p.m. We'll be past the solstice, and hopefully it will be easier to see things. But it was pretty good tonight, right? Yeah. Awesome. Cool. Well, have a good night. Get home safe. Thank you so much.